All right, so this has been a little bit delayed, but as you may or may not know, I'm a strong proponent of releasing code for papers, or at least enough code, pseudocode at least. That's what, for example, the AlphaZero work did. Well, it's not really pseudo; it's more like quasi Python code is what they did. And so, yeah, there's a previous video that I've made called, I don't know what it's called right now, but it's about this paper when it was submitted to a NeurIPS 2020 workshop. Let's see if I can find it right now. Here it is. Oh, it's just called this title 7 months ago. And now the paper has been released, published as part of the volume 148 of the Proceedings of Machine Learning Research. You can find it online. It's on the PMLR website, but it's also on archive. I put a version up there. Both of them are, readily available, so, or open, access, so you can get both of them. I'll link them below. But basically what I just wanted to do here was quickly review the results basically of this, since in the introductory video 7 months ago there wasn't really any results. It was just a proposal. And then I also want to share specifically the hybrid code. I'm not going to talk about or do anything or put out there any code for like the DQN or anything, because I mean there's like 10,000 implementations. It's easy to find. It's easy to find that, but it's not easy to find the quantum code, which is why I'm releasing it. Although when I wrote it, it was kind of challenging, but now getting a lot more experience with the custom layers and such. If you've seen the 3 videos now that I've made utilizing re-uploading and custom layers, this is probably like easy peasy. So this is, the first pages are pretty much the same as the workshop. I mean, slightly changed, but so yeah, introduction, who needs introduction, right? Yada, yada, yada. Background, we all know about the background. So basically what we just want to get into here is, and this is something that's maybe not superbly conveyed in the paper, but was the exact architecture. So basically, right, this is the QCNN, right? The 2-qubit unitary. This is what I'm just going to call the dense quantum layer, and that's a pooling circuit. So basically the idea, sure, I'll draw it right here, I guess. So the idea was you have the pixels. I'll do it up here actually. Sure, we'll do it right here. So you have you have your frame stacked, right? Little things right here. So you have, this is your 84 by 84 by 4, right? Frame stacked observations from the Atari game. I should say, this is kind of, you can read all the introduction and stuff, but this is kind of getting straight to the meat of it, ignoring that stuff. That goes to your classical network, which then goes to this, I'll do quantum dense, Q dense, which was described right here. And then this goes to QCNN, which goes to, and depending on the exact depth, right, you can vary this. But the idea is QCNN to pool. There's no pooling if it's a small enough circuit, to Q dense, to either, now this is where it is variations, right, to the expectation value. Actually, I shouldn't say there's 2. This either goes, right, to the expectation value of the Z operator, and it could go to dense, a classical dense layer. So that's basically just to give you an overview of the system that we're talking about here. For the experiments, right, you can see the variations. So there's this is the what's called the encoder. This is all the number of qubits is in there, and this is the output type. So you can see there's two types of encoders here. There's the dense, which is they're pretty self-explanatory, right? This is a dense neural network, densely connected layers, I should say. And it could be convolutional. The number of qubits, pretty self-explanatory. The output, quantum, means you just directly take these z expected values, and then you use those as the state action, q value, or you can feed these z values into a dense layer and then take that output. So that's what that means. So these are the 12 main variations. You can see the exact experimentations that we did, and you'll notice I didn't call this replicating because I'm not going to run anything. Running this takes a lot of memory, a lot of time. I think I specify down here, let's see, yeah, on an 8 CPU machine, and my current laptop right now that I'm recording this on is 1 CPU, so a lot smaller. It took anywhere from 15 to 80 hours really. These are approximate. Maybe it was only 70 hours. I don't remember now. And currently, although CUDA support is in the works for TensorFlow Quantum, it only works right now on CPUs, so that's why this is all trained on CPUs. So yeah, and you might notice this isn't really important, but originally there was talk of using an initialization strategy proposed by Grant in 2019, but here I saw we ran the experiments and then looked at the actual variance of the gradients and saw that unlike the this line is extracted from that Barron Plateaus paper, unlike that, right, which gets really bad at 15 qubits, you can see the variance really isn't that bad. I mean, 10 to the negative second is definitely workable. And so that's why we didn't use that strategy. The results you can see here, you can see classical learns. You'll notice the reward is a lot lower, and that's something I discussed, and that's because breakout is, the DQN implementation is not like 100% optimized for Atari. There's so many little tips and tricks that make everything so brittle. So you can see one of them succeeded, but a bunch, so like one of them went way up here, but then a bunch just went way down here. And so that's why the average is here. And you can see the Pong, right? You normally see graphs. It would probably look something like this on a normal one, but you can see this one goes up faster, but doesn't go as high. And that's just little tricks of the implementation. I didn't think replicating the perfect DQN results was especially important, considering the relative performance of the, like if these were doing better, then I would value that more, but it's really the comparison that matters. And since even this version, right, that I was working with, this implementation I was working with was probably suboptimal, it doesn't matter because it's in comparison it still performs much better than these. And so yeah, basically the takeaway here is, I should say, I'm kind of expecting you to have seen the previous video because I'm kind of not talking about the setup at all. But on the two Atari games, all quantum systems, you can see this nice little legend right here. All of them are right in here. Maybe I can zoom in. There we go. All of them are right in here at 0. Can't learn a thing. So yeah, basically, I mean, the title's kind of clickbait. I admit that. Playing Atari with hybrid quantum classical whatever learning is kind of clickbait because you're not playing Atari, or at least not very well. But because I submitted it, or we submitted it to the did a workshop and then you weren't like supposed to change a lot of the beforehand. I didn't know if we were allowed to change the title, and I don't want to like get like disqualified or something for changing the title, so I left it. But and I thought about changing it for archive, but then if the archive title is different, then that messes everything. So I just kept it. I just kept it the same. But I don't know. I understand that it's kind of clickbait. And so down here we can see that this is comparing. I've previously discussed this, the results from the the A20 paper. I don't know why I just drew that line. And you can see it does, the hybrid system we present here is capable of learning, just doesn't seem to learn on Atari. Perhaps, and we make this argument here. Ooh, I just noticed these zeros got cut off. I never noticed that before. Perhaps because it lacks the expressive power. You can see when small neural networks, they also fail. But really, that's not what this is. Excuse me, that's not what this is about. This is about the code, which we will now get to. Let me just scroll up to the system. This will probably be nice to. There we go. Here we are. There we go, zoomed in. All right, looking good. So this is just the quantum DQN hybrid setup, whatever you want to call it. This is just the code for that class. If you want to run the actual like experiments, you can use your favorite wrappers for Atari. You can use your favorite logging system, TensorBoard, weights and biases, whatever. Or you could probably just copy the code from my previous RL videos, right? You could go to variational quantum policies and just copy the if name equals main code, and it would probably work. But and pick your favorite replay buffer. I just used the one from spinning up or stable baselines or something like that. So we have our I don't know what this means. Can't make. Yeah, I don't think I'm gonna. I don't know enough regex to interpret that, but in this initialization, right, we have the action size for Pong. I think it's 6 and breakout is 5. I want to say, maybe they're both 5. The encoding type, the number of qubits, and the output type. So we just keep track of these. We make the network and the target. We share weights. We have a size 1 million buffer. We use a batch size of 32, gamma of 0.99, epsilon of 1, the K frames. I mean, these are all just changed. I don't remember if these are the exact same that's in the original paper. I just, when I was writing this code for the to upload, right, I put these values in, but these I know are the same. I don't remember. This one might be different. Epsilon min, that's the same. So that's the minimum decayed to. Learning rate, the classic atom with 3e negative 4. Tau, right, for polyac averaging for the target and current network is set to 0.001. You'll often see this 0.0005. Doesn't really matter. I can put it at 5 or 1. We update the target network every 10,000 steps. So now these are just straight. You can find them exactly online. The 1 qubit unitary, the 2 qubit unitary, the 2 qubit pool, the pool circuit, the quantum commissary, right? Those are already written. I just use existing implementations, or really, yeah, I just use existing implementations. I don't know if I've actually discussed the quantum convolutional neural network or circuit on this forum before, but if not, you can go to the tutorial on TensorFlow Quantum, and it's pretty good. You'll be able to understand it. This is the Q-dense layer, right? I don't know why I always do append instead of plus equals for circuits. That's just always my go-to, I guess, but I feel like plus equals is probably cleaner. This is some real jank and not very understandable. You know, where the hell did I pull these values from? But the idea is basically, I mean, you know what this is creating, the RX or YRC, then C naughts, and then more on every qubit, right? Yeah, you can see for each qubit it does this. And then more entangling C naughts at the end. To make the encoder right, we stack two of these layers on top of each other. And then to make the whole network, right? Before I get into that, I'll talk about the hybrid, right? This is something you probably have seen before at this point, but right, because we have the setup such that the classical neural network is providing some, but not all of the parameters of the quantum circuit. We have to use a custom layer. So we have this encoder, and then we have our adjoint differentiator. We have our, if the output is dense, we have another dense layer. The number of parameters is just the length that we're fed in. We create the trainable parameters. So really, I should probably make this 1 by num_q params. I'd probably reduce an operation down here. But then as usual, right, we get the batch size. We get the input, right? So this is feeding it. So we have our classical neural network encoder, right? So we feed it the inputs, which is the frame stacks directly. Then we get the, oh, I guess I expanded dimensions here, right? This operation is actually unnecessary if I just put a 1 right here. I did, 1 comma, but I don't want to break anything. So I'm just going to leave it. But yeah, this is unnecessary. And then we tile these weights to match the batch size. We concatenate them, right? Because that's all we have to do because we have this. Maybe if I go over and draw this on the paper, we can see. So right, so we have our circuit, right? So we have our, this is our whole circuit parameterized by a bunch of different, operations, right? Whatever. And so these are controlled by the encoder, and these are just directly like updated. I don't know what to call them. Update. So we want to, if we're considering the weights for the circuit, we want to concatenate the encode with the normal. I'll just say updatable. Right, and so that's exactly what we're doing here. Well, we tile them first, but we concatenate them, and then we tile that blank input circuit. We get the quantum output. I think it's interesting that I define the ops. Oh, no, that does make sense to me, actually. I was going to say, why did I define them outside of it? But I'll explain that in a second. And then if the output is dense, we feed it into a dense neural network, and then get the output. And so that's the whole core of the system right here, is all that's going on. And so now we have to talk about what's going on, what's going on right here, right? What's in this circuit? So if we go down, we can see that we create our symbols. I'm just going to focus on the biggest system, I guess. That's probably the easiest. So we have our symbols. Ooh, that's a lot of symbols, right? Thank God for adjoint differentiation, or this would take like 10,000 hours. A lot of them are controlled though, so I guess that's not really that slow. Then the free params. This is hard-coded because I actually just did the math for how many encoded parameters there are. So, this isn't very flexible code. It's very much hard-coded for these experiments. We make the encoder, which I showed the code above. We get the readout ops. And this is just adjusting depending on if the action space is smaller. We don't care. about these extras. I think this is because there's like superfluous action space in Pong or something that I have that there. We make the convolutional quantum circuit, the pooling, the convolutional, and then the dense circuit. So this is sort of the architecture, right, that I presented here, right? We have, actually there's another, in this example, I think this is probably what it's like for the 10 qubit or 5 qubit. We have another QCNN here in this example, but this is what you see, right? Dense, QCNN, pool, CNN. So that's what we see here. We create the classical encoder, which I'll show you right here. It's just a neural network that's just some dense layers or some convolutional layers. That's all it is. Pretty like really simple setup. And then we get the full circuit. So we take the quantum encoder, add it, right? And this is how you can just add circuits because each of these are circ.circuits. So we have the quantum encoder, we have the convolutional layers, which also includes pooling, and then we have the dense layers. And then I'll print each of them. We get the input, which is the 84, We create the model, so we have our free params, right? Because these are the ones that we need to actually keep track of in this layer, right? These are the quantum weights. And then we have the full circuit, we have the readout ops, the classical encoder, the output type, and the action space. We make this model and we return it. Remember, we just keep track of the, this is how we keep track of, adding things to a replay buffer to get the action. We pick a random choice with probability epsilon, and then if not, then we get the argmax, right? The maximum value predicted by the network. This updates to target. This grad update, you can add the TF function flag. I don't, because then printing tensors in a graph like functionalized thing is really bad. But I'll go through this in more detail in a second. And then the train, and then that's it. So it's so annoying when the highlighter does that. There we go. So to train, right, we sample states, actions, rewards. I don't know why I called that variable res, next, and done. From the replay buffer, we normalize the states and the next set of states. We convert them to tensors of the appropriate data type. We get the update, and then we shift the Q target network as need be. And so now for this grad update, right, we do typical Q learning. We get the next target values. Doesn't really matter what's going on here. We get the reward. We do 1 minus dones. So if it's done, this is going to be 1, right? And this will be 0. Multiplied by the gamma, multiplied by the next Q. We get the current Q network's predictions for the state batch, right? Because this is a target on the next state. We get and so these are for the actions, right? That was taken. We get the actions. And then we get the error between them, and then we update the gradients based off of that. So now I'm just going to explain why this line is here. That looks kind of confusing when adding all the tensors, but I'll show you by actually running this code. I'm just checking other code that I have running right now. So yeah, you notice the environment is called JAX, but it's not JAX code that we're running. So if I do Python, it's gonna load for a second, split out a huge bunch of information. It might take a second because I have a bunch of stuff running. There we go. So let's go through the circuit diagrams first. It prints out 2 of them because it makes the target and the Q network. So you can see the encoder here for a 5 qubit example, exactly as described, in the paper. The convolutional circuit is kind of hard to read because it's so long, it wraps around, but you know what the diagram looks like. And the ending is pretty much the same up here. So, I mean, these are exactly the same as the diagrams in the paper. So now we walk through the actions. It's just to make it easy. I was having sometimes TensorFlow, like index operations are a pain. So this I just did to make it work, right? This is the value, the index, and this is the action. So first we can walk through, right? So we have the target queue values that we did by plugging the next states into the target network. That's a nice set, right? 32 by 5, 32 batch size, 5 action space. We take the max, right? So we can see the max here is 0.361. And so we see 0.361. So we get the maximum of those values. And then this is added to the value. I should probably specify what's going on here, right? These are just random values I'm putting in. There's nothing intuitive about them, and so they might not look like the actual values would if I was feeding in Atari information. But yeah, so they're just randomly generated, but they give you an example of the shape and stuff. And so then we get the predicted Q values, and we take the action, right? So let me go back up. The action is the third actually, because it's starting at 0. So we get the third action, which is this one. And then we collect all of those. You can see 0.00149, which is right here. And then we do mean squared error between this tensor and this tensor, and we get this number right here. We do a gradient update, and then yeah, that's pretty much it. And so now I'm going to go back. I'm actually going to delete this code so I can upload it. I don't like having that information or that stuff in the uploaded code. I'll clear out all the print statements so it's actually runnable. You don't want to print them out every single time, right? These are worth having, so I'll just comment them out. And yeah, that should be good. I think that's all the code. But I guess do that. Basically, I mean, I spent a lot of time on this section, which didn't really matter. What I wanted to talk about was this setup, and really it's pretty straightforward. Especially if you watch the variational quantum policies video, the re-uploading video, or the universal qubit approximation video. But even if you haven't, right, the idea is pretty simple. It's just using custom layer to manage this information. You can run this code, or you could, I mean, you need to do a little bit of setup, right? But you could run it, and you could, spend a lot of time to get not interesting. Well, I shouldn't say not interesting, not well-performing results. They're still interesting. And so, yeah, or you could try different things. Maybe try some data re-uploading. That's something I mentioned in discussion. Yeah, for more information, you can always just read the paper. I didn't really discuss it at all here. I just sort of blitzed through it to get to some code, and then I blitzed through that. But I'm going to make this ahead of time. Last time I made a video after I got like 15 different emails, and I didn't want to have to respond to all of them with the same thing. So I'm going to make this beforehand. So it's ahead of the curve. So yeah, here's the code for the plain Atari with hybrid quantum classical reinforcement learning.